Everybody, I hope that you can hear me and see the screen. Can you hear me?
Yes.
Oh, okay. So let's start our analysis that we partially started last Friday regarding the accelerometers and their working principle and how we can use them. Remember, we start our analysis by emphasizing the PZT effect. That is, once we got the piezoelectric crystal, it is possible to stress this crystal so that we can have a sort of generation of electrical charges corresponding to a given plane when the PZT is excited by an external force. By the way, the reverse effect, the actuation effect, is just having excitation from the electrical point of view through charges, and then we can have a reaction of this PZT just by exciting the surrounding structure with some force. However, for the PZT used as an accelerometer, we use this effect, and we also represent this PZT as a capacitor, electrical capacitor, from the electrical point of view. Last Friday, we considered these two equations together, and we found out that if the external force is because of the acceleration that your PZT crystal is having, then it is possible to relate the output tension, that is a differential potential that the charges are having when the PZT effect is putting them on a given plane, and the acceleration, that is x double dot j. We are having said j whatever direction, and that is very interesting. So we can have that the output tension is proportional to the unknown, the acceleration that is characterized in your physical point. However, we end the class saying that that is very nice, but what if now we close the circuit? That is, we need to measure the output tension through a measuring device. So if we close the circuit, then it could happen that all the charges flow through the circuit, and therefore the resulting differential potential is no more there, and therefore your information is completely wrong with respect to the information that we'd like to have as the acceleration that we'd like. Okay, so we have to, so if we are measuring circuit, we need to measure the then the charges Q will flow through the measuring circuit. Okay, thus the output tension is not constant. Okay, so we need to be sure that what we are measuring is referring to the actual acceleration, and we have to take into account the measuring circuit itself. So first, a very high impedance is needed. Okay, just to be sure that we have almost an open circuit condition, measuring condition. But how we can achieve that is not that easy. As a matter of fact, the most important parameters that we have to take into account in taking the acceleration measurement are the capacitor and the resistance of connecting cable, of the amplifier that is there, and of course the capacity and resistance that are intrinsic property of the piezoelectric crystal. So we can review that as the equivalent circuit that could be viewed as, let's say, the PZT crystal is there, and we can view that as a sort of generator. Okay, then this PZT crystal is characterized by a capacity, so viewing that as a capacitor, and also an internal resistance, RQ. I denoted the subscript Q of the charges because of the PCT. Okay. Then we have to consider also the equivalent capacity and resistance of the cables, subscript C, and finally the capacity and the resistance C, A, and R, A of the amplifier that is at the very end of your measuring chain that is there to let you know what is the output. Okay, so the overall capacity of such electrical circuit is very easy to find out because we have a parallel configuration of capacitors. That is, the total equivalent capacity is the sum of all these capacitors. So we have the total capacity of the equivalent circuit is given you by the summation of the capacitor corresponding to the PCT, the capacity corresponding to the cable, and the capacity corresponding to the amplification stage. Yeah, parallel. Now we will see. Okay. Now the reason why I am showing you that circuit, that electrical circuit, is because those parameters are the most important one. So in order to characterize that measurement, the acceleration measurement using PCT, you have to refer to this circuit. Now what we'd like to have is the equivalent circuit. The equivalent total capacity, because the capacitors are in parallel, then it is the sum. On the contrary, the total equivalent resistance of the parallel resistances is 1 over the summation of the inverse of the resistances. Okay, so the total resistance of the equivalent circuit is 1 over RQ plus 1 over RC plus 1 over RT. Okay, and if you like to have, you got RQ RC A divided by RQ RC plus RC A plus RQ A, and that is the final result. So with this model, with this electrical model in mind, that is your PCT material, the PCT crystal is, because excited by external loading, the inertial loading, okay, is reacting to that by generating some charges in some planes, and these charges could be viewed as the electrical charges that are flowing into the measuring circuit. The measuring circuit could be viewed as composed by 3 main components, and those are the most important ones. The inherent capacity and resistance of the PCT, because there is also a charge flowing through the PCT crystal, the capacity and resistance of the connecting cables, and the final amplifier stage. Okay, that is because the capacity is a very, very, very small quantity, very tiny quantity. That's the reason why we have to take into account such three components. However, with this assumption of the circuit and having the value of the total capacity and resistance, the equivalent circuit is this one. So we got, once again, the PCT crystal that is generating your electrical charge, and we have the total capacity and resistance of your circuit. Of course, CT and RT takes into account all of the three parameters, three, let's say, components that have to be considered in this mission. So what happens? It happens that we are having the charges generated by the PCT material, and then once they are generated, are flowing through this equivalent circuit. And therefore we have a discharge of these charges from the positive to the negative side. So the output tension will vary. It will start from the maximum to 0 at the end of the effect. If you solve this circuit, you find out that the output tension is a function of time, and it could be written as P0 times e to negative t over RT CT. Okay, that is the exponential attenuation of the voltage that could be measured. That is characteristic of first order system. If you write the differential equation associated with this circuit, you find out that you have a first order differential equation, and that is a typical solution. By the way, we define tau as time constant. This product RT times CT, okay, so that the previous equation could be rewritten as Vt equal to V0 e to negative t over time, and that is of very important for our analysis. Why that? If you, just to show you what is the effect, let us now plot this behavior, the output tension. Okay, so we can use the y-axis, in which we report the output tension as a function of time, and of course the x-axis, the time. Okay. As a matter of fact, that equation is telling me that the output tension starting from a value, maximum value, V0, when time is equal to 0, is attenuating following an exponential law like this. Okay. Now, if you think for a while that this is your measurement of the output tension, when your accelerometer is subjected to a constant acceleration, you easily see from this picture that if time passes away, then your output tension is no more representative of your acceleration. The actual acceleration could be represented by V0, that is the starting point, that is the value of the output tension corresponding to the charges that the piezoelectric crystal is generating at the time of the acceleration that is exciting it. Okay. Therefore, here what we got is that after a while we have the output potential that is not good at all. So we are in trouble, actually, because the output tension, the measured amount, the measured quantity is not representative. That is true if the time evolution of your acceleration, okay, is, let's say, much slower than the typical time of such a function. In order to characterize the typical time of this function, let's consider this very well-known graphical consideration. If you start from t equal to 0 and you draw the tangent at its value, something like that.
Professor, excuse me, are you writing something? Because I cannot see anything.
Yes, I'm writing something, and you should see something because yeah, we got
There's only dotted line.
yeah. Okay. So what we can see is there we can prove that this tangent line when time is equal to 0 is passing through the x-axis at a time t that is just your constant, time constant tau. Okay. And the value of the output tension corresponding to a time equal to the time constant is about 0.36, the maximum value is. Okay, of course, that is not true from the graphical point of view, but the values are real. So what does it mean then? It means that if your acceleration is characterized by a time evolution that is slow enough, or if you want reverse, if your measuring circuit is characterized by a time constant long enough, okay, then you can have measure quantity, the output potential V, that is quite representative of your time evolution, your acceleration. So you have to be sure that the time constant, okay, is very, very high with respect to the typical time representing the evolution of your acceleration. Okay. And the time constant is telling you what is the reference. Okay. And this time constant is dependent on the visual circuit. So it depends on the cables, depends on PCT, it depends on the amplification stage. So the time constant tau must be much larger than the time required to measure the acceleration x double dot. Okay. But what does it mean then? It means that if you consider the relation between the length of a time domain and the frequency domain, that is one over the other, that means that your frequency, the characteristical frequency that is 1 over tau, okay, should be much, much less than the typical frequency of your time domain acceleration. Okay, can you see that? So that's the reason why, because measurements that are slowly varying in time are critical. That is, they are not major high confidence. Why that? Because if you let time passing by, then the output tension is practically zero. So you got noise. So no accuracy at all. Who is telling you what is slow or fast? The time constant, tau. Okay, so tau here, that is, remember, given you by the product of the equivalent resistance times the equivalent capacity of the overall circuit, the equivalent circuit, is telling you whether or not your measurement is good enough. That is, if the time evolution, once again, of your measurement is low with respect to the time constant, then you got good measurements. On the contrary, noise. Okay. If you see now this concept from the frequency domain point of view, then what you can see is that time signals that are characterized by very low frequency are hardly measured by the accelerometer because they need to have high frequency content signal. Who is telling you what is high and low? The high and low is told by the time constant tau. Okay, tau or 1 over tau if you are referring to the frequency. So tau could be viewed as the period of your measuring time. Okay, 1 over tau is the frequency. Okay, and that is very important for accelerometers. So accelerometers actually can measure the acceleration, but you have to be sure that the frequency content of this acceleration is high enough with respect to the minimum one that is given you by the accelerometer itself. There are some, as you can see here, also yeah, the very top. As we can see from the general circuit, reference circuit, now the page is refreshing here, okay? If we are having an alternate acceleration, then we can have that the Q, the electrical charges, could flow from the positive to the negative plane, far and so on, okay? Because of the sign of the acceleration. If you think to a sinusoidal signal, then the acceleration is going down and up, positive, negative, negative. And therefore you will have positive and negative charges, and therefore you will have as output tension that is positive or negative. In order to reduce as much as possible some error, some noise, and in order to increase the quality of the signal, generally these piezoelectric crystals are compressed so that we have a bias of the charges. So accelerometers are already in a charge state. And the evolution, that is the effect of the external force, the effect of inertia, are superimposed to this bias charge. That's because we are doing that, we can have charges that are always positive or always negative according to the plane that you are considering. And there is a sort of perturbation of this value, but not changing the sign. So there is not a flow, electrical flow inside the PCT, and we have in that high accuracy transducer, just because we are having the charges that are still remaining the same plane, not moving at all. Okay? And that is the typical manufacturing configuration in which we are having a pre-charge of the PCT material in order to have operating condition in a practical linear game. Okay. And the reason is that the charges are not flowing from positive to negative, so there is no zero crossing, and so we are increasing a lot the accuracy, we are increasing a lot the life of the accelerometer, and we are increasing a lot the linearity of the accuracy by itself. Okay. I just want to tell you that there are some manufacturing techniques of these accelerometers that are capable to sell this accelerometer of the size of, let's say, 1 millimeter cube or 1 millimeter edge. Okay. And so these are miniaturized accelerometers. And for such accelerometers, the mass is, just to give you an idea, less than 1/2 gram. Okay. We are also having triaxial accelerometers. Okay. Which the mass could be less than 1 gram. And concerning the dimensions, the first one is about, let's say, 3 times 3 times 3 millimeter in size, and this one is 7 times 7 times 7 millimeters. Okay. The other point is that if you go back to the basic working principle, such an accelerometer will create an electrical charge, okay? And therefore you need something to measure this charge and therefore transduce this charge into an output tension, differential potential. You can easily see that it is not that convenient from the practical point of view, because it's not that easy to measure the electrical charge. We can do that, and we have some transducer that are able to do that. But most of the time, it is better to have your transducer with an output tension as the output quantity, electrical quantity. So it is possible, and the manufacturer made a lot of progress in doing that, to miniaturize also sort of amplification stage inside the accelerometer, so that we can have what we call ICP accelerometers. That are included inside the accelerometer a small integrated circuit that is transducing your electrical charge directly from the PCT into an output tension, so that you can plug the output the cable from the accelerometer that is in volts straight into your measuring circuit, okay, that is covered to measure volts. So without having not having the need to measure the charges as a first step, okay. And these are called ICP accelerometers that are integrated circuit PCT. Okay. And they having such a characteristic. Of course, you pay the cost of having less accuracy, okay, with respect to the charge accelerometers, okay, because the charge accelerometers have, let's say, the maximum sensitivity, the highest accuracy, okay. The PCT the ICP-based accelerometers are in fact very useful, very handy, and they are not that accurate as the other one, but we can use that every time. In the laboratory, we are using those accelerometers. Let's see now, yes, two configurations, okay? So general configuration. We have the compression, acceleration, and the shear configuration. Two main configurations. Let's see first the compression one. The compression one is composed by, let's say, a base. To this base, the PZT is attached. Okay. Then there is moving mass. M. And this moving mass is attached to the PZT through a mechanical stiffness, if you want, also a damping. Okay. The moving mass is the one that is sensing the acceleration. Okay, can you see the operating circuit? We have the mass that is sensing the acceleration, and this mass is connected through a stiffness and through a damper, C, through to the piezoelectric. Okay, and this piezoelectric is bonded to the base stack. Then we can have also some circuit. Integrated circuit, let me call it here, and everything is sealed to prevent any damage, corruption, and so on. Okay, and therefore you have the output, okay, somewhere. Okay. Now, let's see the shear configuration. The shear configuration, what we got is the PZT crystal that is cut to emphasize the shear behavior. Okay, so we have something like this. Right? No, sorry. Okay, never mind. Just a change of colors. Okay, this blue here is your PZT material. Okay, as you can see, the configuration is completely different. The crystal now is cut so that to emphasize the shear. So it's a sort of shell of piezoelectric material to which is connected a mass. Okay, and this mass is here, and everything is connected to the ground, okay, through stiffness and tamper like this, and everything is sealed once again. We have an integrated circuit, and everything get out from here from the electrical point of view. Okay. These two layout, although they are working the same in principle, they are not from the practical point of view. Why? The first one, the compression one, okay, is very sensitive to external factors as the operating temperature, okay, base deformation, okay. These at least are the two at least important parameters that have to be considered. They are used mainly in sharp measurements, okay, that is measurement characterized by very high level of acceleration that are acting on the structure for a very short time. Okay. The shear configuration is more stable than the base one, the compression one, okay, could be easily miniaturized and is having a high sensitivity compared to the compression one. Okay, so these are the two typical layout of the accelerometers that are using the same PZT crystal, but one cut so that it works in compression traction way, the other works in the shear way. Okay, by the way, the accelerometers that we are going to virtually use in the laboratory activities are all shear accelerometers. Okay. We can have maybe 5 minutes break, and then we resume the question from home. Okay. Are you from Maryland? Yeah. Where exactly? Okay. Okay. I was there, University of Maryland. Oh, okay, yeah. 10 years ago, you more. Yeah. Okay. There is a professor that I know very well, my colleague, is Ingrid Chopra. I don't know if you know him. Yeah, he was in a helicopter. Has some activities, not with him, afraid in some people within, but yeah. Yeah, just for visiting these colleagues there. So few days I've been there. But the fact is that when we, we met actually during the conferences once or twice a year. So after 20 years, we know each other. I think now he's retired. I think. Well, Jorge, don't worry. I will share the documents. Okay, with you. It was planned to have a conference in 1st of January in Nashville, so not far. No, everything is virtual now. It's the AIAA conference, American Institute of Education. It's a huge conference, more than 5,000 people. Yeah. There were lots of them. Now everything is slowed down. Yeah. Yes, there are, but everything is virtual. Last time the conference was just 1 year ago in San Diego. Yeah, January 2020, just before the lockdown. Oh. January 2020. I got a time just to come back home. Yeah. Yeah. It's a week actually. Conference lasted 1 week. It is very nice because we meet a lot of friends from all over the world. We make connections. I mean, with these talks, a lot of my students going around for degree thesis. So it's very nice. Yeah. Uh, this year, yes. Yeah. It's not the same, of course. No. You stay there just for presenting your paper and then doing a lot of things. That's the way. We would see. Maybe we will have the medicine, the last thing. Maybe. According to your president, there's no need of. We will see. Okay, let's resume the class and let's see the accelerometer from the global behavior point of view. What does it mean, global behavior? If you remember, for example, the behavior of the, let's say, rheostat or whatever, displacement sensor, we didn't notice any time dependency, okay? And indeed, we classify such a transducer as a zero order transducer. That is, the differential equation for that is of a zero order. So what is doing the physical quantity is just what is transducing your transducer, okay? Just into the very beginning of our classes, okay? Now, because of the electrical charges that are flowing to the measuring circuit, your accelerometer is no more zero order transducer. We need to have a time evolution that is fast enough in order to be measured by your accelerometer, okay? And therefore, it is very important to characterize the overall behavior in all the frequency domain of interest of your transducer. In order to do that, we can make use of what we call the transfer function of your accelerometers, meaning that sort of relation between the output and the input, that is your output tension and the input acceleration, okay, as a function of the typical frequency content of your acceleration, your time domain variable. So that is written as your ht, that is dependent on the frequency content, is given by two main contributions. The first one is what we call HE, that is dependent on F, and HM. What does it mean there? The first contribution, HE, is the electrical behavior of your accelerometer, whereas the other contribution is the mechanical behavior. Okay, why I'm introducing this mechanical behavior? Because as we saw before, whatever will be your generical layout, compression or shear, we have a sort of mechanical impedance that is connected to your PCT crystal, okay? Having a sort of stiffness, having a sort of damping properties, okay? And the mass that is sensing the motion. So it is a harmonic oscillator. That's the reason why we have to take into account this mechanical behavior when evaluating the global behavior itself. Please note that we are talking about frequency domain behavior. So this star here is just representing me that is a convolution. Okay. In order to have the overall time domain behavior, you have to take the integral, so make the convolution that is equivalent to the frequency domain of just having of the two transfer functions. Okay, but it is better to remember, so that is why I'm using the star. Remember me that it's a convolution between the mechanical and the electrical behavior. So, in order to characterize this, let's have a plot, typical plot of such a transducer barometer. So we have in the x-axis the frequency, okay, and in the y-axis is your overall transfer function, okay, in terms of amplitude. So, a question for you, according to what we already discussed, what is the transfer function, the overall transfer function, when the frequency is very, very, very low? Remember what we said? When the
It
frequency,
must.
yeah, say again.
I think it must goes to infinity because we have 1 over frequency.
Mhm.
We have small frequency, so it means we
So
have.
the period of the corresponding period is going to small quantity or to longer quantity.
Mm,
If f is going to 0, then the period is going to infinity. Okay. Now, what does it mean that? It means that the duration of your time evolution, unknown time evolution, could be, and it is, longer than the time constant. Okay. And if that is longer, it means that your output tension is no more representative because it's going to 0. So, and therefore no measure at all. So the overall transfer function is composed by, let's say, first part that is characterized by this f1, 1 over tau, that is practically very, very small 0, and then goes up to approximately 1. Okay, then goes straight, sort of constant value, regardless the frequency, and then we have sort of amplification like this. Okay, I don't like it much. Good. Okay, something like that. It is smooth, of course. And here we have a second frequency. Let me call it Fm, and then we got about a second frequency. So as we can see, we have 3 regions, operating regions. Okay, the first one is below F1. The second one is between, so first region. The second one is between F1 and F2. And the third one, third region, is a frequency higher than F2. Okay, let's talk about the second region. Okay, the region between F1 and F2. That is the region that I love, the region that I would like to have, because transfer function is unitary. It could be biased, I don't care, but it is constant. So whatever will be your frequency content of the signal, there is a one-to-one translation, okay, of that acceleration into the output voltage without any other corruption, okay? Just a value, just a constant value. Here we got 1, okay? If the frequency constant is smaller, better, lower than F1, that is much longer periods, okay, then we are going to have phenomena whose characteristic time is longer than the time constant. Therefore, we are having an attenuation. We can't have any measure at all. So the first part of that diagram is the one that I would like to avoid, because we have 0. There is a lot of attenuation. We have a lot of noise. Okay, and that is due to the electrical behavior. So let me write here that this region is driven by the electrical circuit. Okay, the first that I present. Then here we got the typical operating region. Everything is perfect, ideal if you want. And then the third one is driven by the mechanical components. Stiffness, the damper, the mass itself, okay? And they could be represented by the natural frequency. Here is Fn, is the natural frequency of the single degree of freedom, okay, mechanical circuit. M, K, and C, just to be clear. What this is doing in your measuring circuit is creating a much higher response than expected. Okay, if you're operating, if your signal is characterized by a frequency that is larger than what I call F2, then the overall response of your transducer is sort of amplifying a lot your responses. That is, you're going to saturation, you're going in overdrive, everything is noise because you exceed the maximum signal level that you are expecting, okay? And that's not good at all, okay? So also the third region, the mechanical one, has to be avoided, okay? In order to have a good measurement. So the first part has to be avoided because of attenuation, noise, okay? The third part has to be avoided because of saturation, okay? Much larger signal than expected, okay? And it is not constant in frequency, the other reason, because you have the peak of resonance over there, so it is no more constant. So, all said, the second region is perfect one, okay? That is characterized by practically a constant line. That is, the transfer function between the output and the input is not dependent on the frequency content, and that's what I like. It is very, very nice. It's just a matter of having the factor that is translating the output voltage into the acceleration, unknown. Okay. Finally, from the measurement point of view, I would like just to add a few words concerning the accelerometers that could be used for the angular acceleration measurement. Okay, just a few words on that, and then I can show you some mechanical, some manufacturing details of accelerometers. So when referring to measurement, the measurement of the of angular acceleration, we are in trouble. And indeed, there is not actually angular accelerometer developed with a very high degree of precision, okay? A way of representing these measurements could be done by introducing two accelerometers, okay? Let's see how. We have the body, the structure here, okay? And let's assume to have one accelerometer that is placed in a position, let's call it A, and the other accelerometer in a position that could be referred to B. Okay, these two positions are put one apart the other by a distance L. Okay, now we are going to have this system, the hosted system that is moving, having a translational and a rotational acceleration, generally speaking. We can use the measurement, the two measurement, accelerometer A and accelerometer B, in order to have the average acceleration, let me call it double dot x0, that could be defined as the average of the two accelerations that are measured by accelerometer A and B, and the angular rotation, so the acceleration, okay, theta 0, that is defined by the difference of the two accelerations. Okay, in this way. Now, what's the point on that? In order to measure the angular acceleration, theta 0 double dot, the measurement of the difference between xa double dot and xb double dot is required, as we can see from the very nice formula. Okay, but if you are interested in the elastic rotational acceleration, that is the point acceleration in the rotational degree of freedom, okay, what you need is that these two accelerometers, XA and XB, are not that far away one each other, okay? In principle, they should be one over the other. That's not possible, of course, but however, what is the requirements is that these two accelerometer are measuring the acceleration almost at the same point. But that means from the equation that because A and B should be close one each other, because they have to measure the same acceleration point, okay, then what is happening is that XA double dot is practically the same XB double dot, okay? Thus, XA double dot negative XB double dot is with very large error. Okay. Because we have to have these 2 points very close to one each other, the two accelerations are practically the same. And when you are evaluating theta 0 double dot, you have to take the difference at the numerator. And this difference is a difference that is taken considering two practically the same quantities. So it is noise. Moreover, also the distance L is a small quantity. So you got noise divided by practically 0. And so the result is very, 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 let's say, with lower accuracy. Okay. Also, L goes to 0. That increases the uncertainty. Okay. So if you refer to this kind of configuration, we have many other configurations, but that is a typical one. Okay. We're referring to the rotational acceleration. If you would like to have an elastic rotation acceleration, not a rigid body, okay, if you put two accelerometers into completely different points, then you can use that, of course, okay, no worries about that. But if you are interested in the elastic rotational displacement, generally speaking, and the acceleration of that, so the rotational acceleration, then these 2 points must be this almost close one each other, same point. The acceleration is practically the same. Taking the difference, we got error because we have two practically the same quantities. Moreover, you amplify this error because the denominator L is also going to 0, and therefore you amplify everything. That's the reason why there is still room to new technology in measuring the rotational acceleration. So if you have such idea, some good ideas, let me know so that we can make money together. Okay? So let me know that. Don't be shy about that. Okay, having said that, I would like to show you some typical configuration of the accelerometers and some application that I've taken from the B&K here. B&K Brewing here is one of the major PCT manufacturer, not only but also measuring circuit. There are also many other, but B&K is one of the, let's say, oldest historical one and very well known. So as you can see here, we got start from this one, and this is the first accelerometer that we saw together. Okay, maybe I can make a a zoom on that. As you can see, we have the PCT at the base, and then we have the connection with the moving mass over there, and then the configuration is practically the one that I roughly depicted during the presentation. And we can compare that with the delta shear. This one, that is the configuration for which the PCT crystal is cut in a shear shape, so they are parallel, and there are three, forming a sort of delta shape. And this one is very insensitive to external noise, and these are very, very important. These are the one that we most use in real life. Then we have, then we have the planar shear here that is simple in the configuration, the manufacturing, than the delta shear one, okay? And we can use this very easy configuration to further miniaturize all the electronics that could be considered inside the accelerometer. By the way, the dimension, as I said, is some millimeters, so they are very, very tiny, okay? And the cost of that is, the delta shear is about, let's say, 1,000 euros plus VAT to me. Okay, if you're going to buy that by your own, maybe you have to consider a little bit more money. Okay, so that is the for the simple one. If you go to more accurate, more precise, then you have to increase a lot the cost. The other configuration is the theta shear, so, and the annular shear. So let's say the annular shear. As you can see, we have also the possibility to include some electronics, the ICP configuration, so that, remember, the ICP accelerometers has the property that the output is already involved. Okay, so differential potential, without requiring the measuring chain to have, let's say, a charge amplifier in order to transduce the charge. Okay, annular shear, theta shear here, and auto shear are the other possibilities that we got. Okay. Operational range. As we can see, according to the different frequency, operating frequency, then we have a different transducer that we can use. Generally speaking, what we got is that in a low frequency range, the PCT accelerometer is not that good. Okay, it starts to be good at higher frequency than, let's say, 10 hertz. Okay, 10 hertz start the operating range for the accelerometers. If you are having phenomena that are characterized by lower frequency, then you have to go to other transducers, strain gauges, for example, velocity or eddy current, whatever. okay, we can use that. Oh. Okay. That is not that good. Okay. Then another parameter that we have to consider when choosing an accelerometer is the weight, okay, and the type of the level of acceleration you want to measure. So we already discussed about that. If you're using an accelerometer to measure shocks or to measure very high amplitude vibration level, then you have to move to base, and so it's compression shape crystal, PCT crystal, and therefore you have to go also to shear shape accelerometers. And the size also in terms of the dimension of weight change, because if you're going to measure very low frequency signals, then maybe you need a seismic mass that is larger in order to go down with what I call F1 frequency, okay? And therefore you have to choose in between your requirements. Okay, and in this picture you have a rough idea of what are the typical weights and sensitivity of your accelerometer. Okay. And here is the plot that I just showed you. Of course, because B&K would like to sell accelerometers, the overall transfer function, okay, is reported so that they emphasize the goodness of the product, okay. So all the part that is lower than F1, as you can see here, is really minimized, okay. But actually, you have to go like that, okay. And this is a logarithmic generally diagram, okay. So please be sure that what you are buying is really what you need and not what the seller would like you to buy. Okay. And the other information is the frequency, the natural frequency of the mechanical system. As you can see, the fact here, we have here the increase of the response of your accelerometer because we are approaching the natural frequency of the mechanical system. Okay, and therefore we have to avoid that part. As a general rule of thumb, we can use accelerometer up to 1/3 of this natural frequency, 0.03 f0, according to the notation. Okay, and when you are having a frequency or operating frequency that is equal to 1/3, 0.3 f0, then you have a distortion of about 10% with respect to the unitary value. So that's the reason why you have to go down with respect to 1/3 of the natural frequency of the system, mechanical system. Okay, so that you are sure that your response is in the second region. Your operating conditions are operating in the second part of this diagram, that is almost constant frequency behavior. Okay. We already talked about size, dimension, masses. Also the sensitivity depends on the dimensions and the size. And in this picture, you can see that if you go to very small accelerometers, then the sensitivity is also very, very small. If you increase the size of the seismic mass, then you can have higher sensitivity and vice versa, of course. And in this chart, in this table, you can see the difference, the sensitivity in terms of picocoulomb per acceleration. Okay, when you virtually be down in the laboratory trying to attach your accelerometer to the test structure, then you have to take into account how you can attach that. There are a lot of possibilities in doing that. We have, as we can see here stud mounting, cementing stud mounting, adhesive tape, and also beeswax. Okay, the stud mounting is the best one. What does it mean? That you have a stud that is interconnecting the host structure and the accelerometers with a screw, some holes, okay? And that is very, very useful because it guarantees a rigid connection between the host structure and the accelerometer, so that you are 100% sure that the acceleration that is measured by your moving mass and therefore by the PCT crystal is the same as the host structure. And then you are done. However, that is not always possible to do, because it is not always said that we can drill a hole in the whole structure and then place a stud there, so change the structure itself. Okay, so maybe for a civil engineer structure we can do that, but not for, let's say, a satellite, not for an aircraft, because we can't drill any holes whenever we like. Okay, and that's the reason why we can also refer to cementing stud. Okay, that is another good approach, a good method to touch the accelerometer into the structure. However, once again, it is not said that the outer furniture is allowing that type of cement. Therefore, we have to be sure that there are no issues from the safety point of view in using different cements. Okay, and therefore we have to check that. So in order to also solve this problem, we can use adhesive tape, okay, or beeswax. The beeswax is the general way in which at the laboratory we attach the accelerometer. It's very nice. It is not an actual beeswax, it's some mineral, but it reminds us the beeswax, and it is very useful because once you put a drop of this beeswax, it is of the consistency of the wax, okay? So then you can attach the accelerometer and the accelerometer is there, it's not moving at all. But it happens that because of temperature, it could melt a little bit, or the connection could be not that rigid as expected, okay? For example, that happened to me when I made a ground vibration test, the measurement of the vibration in aircraft in a hangar in our southern region, Italian southern region, that is Puglia, during summertime. We were at 7 a.m. in the hangar with already a temperature of 35 degrees. So when after 2 hours it go over 40, so we have to stop there, and the beeswax was suffering about a high temperature. So we have to really wake up very early in the morning in order to take the measurements before the heat was us. But after that, we go having, let's say, an early lunch, and then maybe our our snack time. Okay. However, what is the effect of these different mountings on the? Yeah.
Excuse me, Professor.
Say again.
So you said that the cementing, I didn't understand something. You said that cementing stud has a problem. Because of that problem, we go to beeswax, but I didn't understand what was
The
the
problem
problem.
is that because if you have some paintings, if you have some environment protection of the outer skin of your whatever test specimen, then the cementing could alter the physical property of these paintings or whatever sealing materials, okay? And therefore we can't use that. So we move to thin adhesive tape or beeswax. Okay. The effect of the different type of mountings in the frequency of function are here reported. As we can see, the stud mounting is the perfect one, and then we have some changes in the level of the response because of the different connections, as we can see here when using the cement stud or adhesive tape or beeswax. There are also other chances in which we can't even use the beeswax, okay, and then we have to use what we call the handheld mounting. As you can see from these pictures, there are different chances in using that, the reverse one, the handheld, the reverse, inverted, or magnet. Each one has its own frequency response, okay, of the whole system. And as you can see, when you're using the handheld probe, you are in the worst condition when measuring the acceleration. Invert probe and the magnet one are not that bad with respect to the handheld probe, of course. But however, the handheld could be the only possibility that we got. For example, if you would like to have the measurement of the acceleration of a running jet engine at very high temperature, okay, there's no way of having other solution than the hand probe, and you put there, okay, just for a few seconds, you stay there with your hands, and then once you take the measurement, go away. But otherwise, you can have the risk of melting everything because of the high temperature, for example. Okay.
Professor, the magnet mounting doesn't affect the circuit?
Depends on the material, of course. If you are having non-magnetic material, then you can't use the magnets, of course. If you are having something that is a magnet material, then you can use. For example, if you're using aluminum alloy-based material, then the magnet could not be used at all because there's a way of touching with a magnet any accelerometers on the structure. Okay, but if you're using, for example, steel alloy-based material, then you can use that. The effect on the frequency response function is the one that is shown, but however, in the lower frequency range, it could be used. Okay.
Okay, thank you.
Okay. Because we are considering electrical connections, and I remember the PZT effect is based on the generation of electrical charges in some planes of your PZT material. Also, the isolation could be an issue for your accelerometer, and we can use different layouts. Here in these two pictures, we can see the use of the mica washer that is isolating from the possible ground loops your accelerometer, or some mechanical filter when referring to vibrations that are not designed but they are there. Okay, for example, high shocks. Okay, in the first case, by adding mica washer is not altering that much the overall frequency response. Okay, so you can have a prevention of possible electrical ground loops without any influence in your measuring chain. Wherever, when we are referring to the mechanical filter, because we want to filter some undesired vibrations such as shocks, then as you can see, there is a big change on the FRF, on the transfer function, and that requires a lot more attention when using such a isolated mechanical filters. Okay, and that is very, very, very nice example on how you can choose the right position in your acceleration. For example, let's look onto the right of this picture. We have a bearing, a shaft that is moving, an engine, whatever it is, doesn't matter. So my idea, my desire is to measure the acceleration of the shaft and the bearing. Okay. So what are the possibilities that I got there? We can mount your accelerometer in configuration A, B, C, and D, for example. Okay. Now, let's consider, for example, configuration D. Okay. As you can see, D, the accelerometer in configuration D, is placed on the cover of the old bearing and shaft system. Okay. And sort of plate that is preventing the shaft and bearing from the outside environment. Okay, but if you put the accelerometer there in D position, your acceleration, your measure acceleration, will take into account not only of the bearings and the shaft, but also of the vibration of the cup that is used to isolate everything from the outside environment. Okay, so that is not a good position at all. How about B, position B, that is on top to the right? That position is not suitable at all because it will also measure all the vibration coming from the other side, the other part of your whatever mechanical system. Okay, so that's not good. How about position A and C? Positions A and C are good because position A is measuring the, let's say, vertical with respect to our picture acceleration of the shaft and bearing motion, okay? Whereas the C accelerometer is measuring the axial acceleration. Please note that there is no importance of the fact that these two accelerometers, A and C, are not aligned with the measuring reference frame, bearing, and shaft, for example. What is important is that these two accelerometers are measuring the right acceleration, regardless of the position, okay? And position A and C are actually guaranteeing me that the acceleration that is going to measure is the one that is moving, that is characterizing your shaft and bearing system. They are not at the same point, of course, but the transfer function between shaft and bearing and A, position A, is practically a rigid one, okay, as well as is rigid one when referring to C, okay. So that's the reason why positions A and C are the most important, are the useful one. The other are bringing you a lot of noise into your measurement, okay. So when you are asked to measure something, please, you have to remember what is the objective of your measurement and then place properly place the transducer so that you are measuring the right physical phenomena and not others. Okay, and this example is telling you, is giving you some ideas on how to avoid that.
Professor, what was the problem with B situation?
B acceleration position is measuring also all the acceleration coming from the rest of the machine. Okay. So all the connecting part and everything that is not straight related to the shaft and the bearing motion. Whereas the D is measuring the deflection of the plate that is covering everything. So these two positions, B and D, are not good because they are measuring something else with respect to the vibration from the bearing and the shaft. Okay.
Okay, thank you.
Another important thing that we have to remember is that while you are attaching the accelerometer in your structure, you are also mass loading the structure. So, for example, if you are using these measurements to correlate your, let's say, finite element model or whatever numerical model, then you have to take into account that by adding an accelerometer, although with very small value of the mass, it is introducing a mass loading. Mass times the acceleration is giving you the additional forces, or if you want, the additional force, the inertia divided by the acceleration is giving you the additional mass. It is just a matter of using the equation. And in this picture is telling you what is the equivalent mass loading because you are adding something in your structure. Okay, and that is very important when correlating with numerical model, for example. And as you can see, the equivalent mass for a very small accelerometer, the top one, that it is having just 0.65 grams, okay, correspond to 7 grams when vibrating. The mass of accelerometer that is equal to 54 grams, okay, corresponds to 600 grams, okay, when accelerating. And so far and so on. So 5 kilos is just another reference. Almost there.